doing high throughput simulations for tribological systems.
Yeah, thanks. Before we start with the first talk, let's just think about the topic one more time. The topic of this year's seminar was Tribology, Applications of Big Data, High Throughput Machine Learning and Artificial Intelligence. We are now in the third session of the seminar, coming sort of to the closure of this topic. That means we started in the first session with very basic talks about big data. What possibilities does artificial intelligence actually show for further research in our topic? And in this topic today, this session, we will be more actually ending up at the point of really talking about tribology, tribological systems, and where these applications can help us. And with that, I want to already start with our first speaker. We are very happy that Dr. Georg Vorlaufer agreed to give a talk today. He studied in Wien, where he did his dissertation on vacuum and surface physics, and then started off in the software business, software development business, changing a couple of times. And in the end, now he is currently already for quite some time, nearly 20 years, a scientist at the AC2T Research Center in Austria, which is very well known for tribological research. And today he will talk to us about the application of AI or machine learning methods for the analysis of tribological data sets and show us use cases and challenges. And with that, Georg, the word is yours.
Yeah, thank you. So I will share my screen, just a moment. So can you see the right screen now? Probably not. I have to share another one. So let's see this one. So just a question. Can you see my screen?
Yes.
Yeah, perfect. Yeah. So thank you, Norbert, for the kind introduction. So I will be talking about AI and ML methods in the framework of analysis of tribological data sets. And I would like to give my, let's say, talk a bit about hands-on use cases or applications, which we have carried out in the last, let's say, two and a half years here in our institute. Yeah, so I hope it will be interesting for you and you can learn something. We learned a lot, and I will give a very short, let's say, lessons learned summary in the end of my talk. Okay, so with that, I would go into the introduction, and I would like to introduce myself first. So my name is Georg Vorlaufer. I'm Austrian, and I studied in Vienna what is called at the time Technische Physik, which is basically a study of applied physics at the Technical University in Vienna. As you can see, it took me quite some years to complete my graduate studies. That's why, because I was always, let's say, inclined on working with software, and I have starting coding and software development at the age of 13. So that's why it makes it up of 40 years of experience in that field. Okay, then I did my doctoral studies at CERN in Geneva, where I worked on, as Norbert already said, on vacuum and surface physics. So I was always inclined to more to experimental aspects of physics than to theoretical ones. But at ACT Research, where I've been now working since almost 20 years, I switched my focus first to modeling and simulation. So that means I have kind of 20 years of experience in infinite element modeling, for example, or mathematical modeling in general. And of course, tribology, which is our research focus in the institute. Yeah, and since about 3 years, I'm responsible for activities around data science at ACT. And with that, let's say, function or these duties, I would like to give my talk today. Okay, so short facts about ACT research. As most of you might know or might not know, we are one of the largest private, that means non-university tribology research service provider in the world. About 140 employees, and from that about 100 scientists in the different fields, which you can see here, which highlights basically the interdisciplinarity of the research field which we are working on. And yeah, we have a quite large laboratory space and office space. We are running a publicly funding project which is called Tribology, which I will talk about briefly later on. Our approach is basically, yeah, it is what I would call a systemic approach. So we have groups which are dealing mostly with materials, with surfaces and friction, with lubricants, and we have a huge, let's say, R&D infrastructure, which consists of tribometers on one hand, but analysis instruments like mass spectrometry, secondary electron spectrometry, and other high-end analytic equipment. And of course, quite some tradition in multiphysical modeling and simulation. So Michael also did part of his PhD work with us in ab initio modeling. So that's also one of the activities which we have in-house. And what is lately coming more and more important is about digital transformation or digitalization and the related methods of data science. So talking about our publicly funding research program, which is basically accounting for 3/4 of our total turnover, I would say, is we started with the latest research program in 2020, and it's going to end officially in about 1.5 years. But we have the chance for an extension until March 29. And within this 4 years period now, we have some target values, which are about 200 papers, 45 PhD theses, and some master theses. And our consortium is about 80 companies and 40 scientific partners. So just to give you a very short impression what our company partners are. So they are basically well-known companies in the field of production, in the field of automotive industry, in the field of material development, all over the world, but of course, mostly concentrated around Austria, I would say. And our scientific partners are also, yeah, you might recognize one or the other quite well-known institute here. Okay, so that is about a very short introduction about our institute. And now to the, let's say, motivation of why we do data science at ACT. And that motivation has been outlined in this schematic graph here, which was also basically the heart of our proposal for the current research program. And that is that the data is the core of our research, basically. So we are on one hand doing fundamental oriented research, but we would like to transfer this research to some industrial relevant solutions and to answer questions which are relevant for daily life, if you want. And to our point of view, data is the central piece here. And that is the rationale of our activities here. So we adopt methods from data science and integrate them in our, I would say, in our daily research work. And what we consider AI and ML, because that is the specific topic of this seminar series, is that we consider AI and ML as being only one part of our data science activities. And it is a very powerful tool to assist research with large data sets. But we are also aware of some problematic aspects, and I would like to highlight them also, because I think people are often not so wary about these implications. And that is, okay, AI has some current hype, I would say, which is also carried through politics and through marketing aspects, and I think that raises a lot of probably false expectations also. And we have, I mean, there are discussions going on about the ethical aspects of AI and letting the computer overtake too much responsibilities, if you want. So one has to be careful about that. And one other problematic thing in my point of view is that especially deep neural networks, they are very, they are not deterministic in a way that a human can explain them or understand them properly in their decisions. And I think that is a dangerous point, or at least a point where we in research should care about, actually. And then at the third point, which I would like to highlight, is that AI and other data science methods, I would say, are inductive in their nature. So that means when you think about the philosophy of science as put forward by Karl Popper, for example, then this is an apparent conflict, and we should deal with that. We should be careful on how we use AI in our research. But that said, again, it's a powerful tool. It can help us to shorten, for example, very complicated computations, as we have heard already, and it is a tool to assist our research, and we should use it properly. So that said, a short overview of what we do in our data science activity at ACT is, of course, we have a huge part which is more or less the generic or classical data processing, which goes from data acquisition to storage management. And I will tell you in my lessons learned statement that this is something which is not to be neglected. And of course, all the data preparatory steps like filtering, outlier detection, visualization of data, this is a huge topic which takes resources and takes time. So that is something which for us is very important. Then of course, statistics, let's say what I would term the mathematical or the classical statistics is a very powerful tool as well. And a lot of modern developments go on here into, for example, robust statistics or regression methods, which are very advanced. Also the topic of designing experiments, the topic of clustering and exploratory statistics like principal components analysis. That is something which can help us to deal with this data which we have. And I will give you an example about that later. And then, of course, the actual topic of machine learning in AI is also part of our research or our activities. And here we have adopted methods from supervised learning and unsupervised learning. And I will also give you an example about that. Okay, so that's about my introduction to the topic from my side. And now I would like to switch to the application examples as promised. So I put together 3 use cases or 3 application examples which deal with all the 3 aspects of data science which I have mentioned before. These are all published results, so I will give you the references to the relevant papers at the end of each of these 3 sections. And we start by looking at what I would say is the foundation of data in tribology, and that is tribometer experiments. And here specifically about the pitfalls or the intricacies of doing tribometer tests, and that is the dynamics of the machines themselves. So if you look at a typical, this is really a prototypical tribometer, is a pin-on-disc tribometer which has a rotating disc, and a pin which is pressed by a loading mechanism against this rotating disc. And then you have typically a force measurement which is measuring the normal force and the friction force using, for example, a cantilever or other system. You often also have some kind of displacement measuring device which would give you an indication about the total wear which you have already produced. But and this is a mechanically seemingly very simple machine, yeah, but it is not as simple as it might seem, because the disk is never completely flat, and it is probably not even possible to mount it in such a way that is completely, let's say, the surface is normal to the rotation axis. Yeah, so it has a certain tilt and it has a certain waviness. And if this disk spins fast enough, it will give rise to some dynamic excitation of the system. And if you are unlucky, you will run into one of the eigenmodes or the eigenfrequencies of this system, and it will behave in a way which will basically shadow your actual measurement data. So it means that the friction force and the normal force, for example, is actually what you measure is a contribution of the actual contact forces you have, but then to some extent also the dynamic forces in the system. And if you analyze these kind of signals carefully, you can actually separate some periodic features from the actual, let's say, signal which you want to detect. And if you do that, you can actually reduce what is an apparent noise in the signal. So here again, the schematic view. So we have a pin on the disk. We have some sponge which applies a certain defined amount of lubricant film on the disk, and we have a sensor which indicates the zero position so that we can detect the number of rotations of this disk. The core thing here is that you have to acquire the data at enough high sampling rates to resolve, let's say, the individual cycles. So that means if you have, for example, a 50 Hertz or 3000 RPM rotations, then you need at least, let's say, 5 kilohertz sampling rate to resolve in a reasonable way the individual rotations. And when you do that, you can group and split the data on a cycle basis, and you can employ different data analysis techniques to visualize or to analyze what is happening dynamically in this tribometer. So here, for example, what we have here is on the left side of this slide, you see what is called a periodogram, or a output of a time frequency analysis, which reveals, on one hand, the parallel lines, which you see here are basically the harmonics of the rotation of the disk itself. And then the vertical lines would actually show you different regimes of operating conditions. Yeah, if you have a lot of noise, that means the system is running unstable, then you would see basically frequencies appearing or amplitudes appearing at each frequency. And if the system is running stable and clean, you will basically only see the harmonics. So this is a very important visual tool to help to understand what is going on in the experiment. On the other hand, what you can see is that you can basically, on a cyclically resolved or time resolved basis, you can see how the system evolves over time. So tribology or tribological testing is always combined with some certain run-in period where the two surfaces have to adapt to each other, and then to go to some state where the system behaves stable, and normally this is accompanied by a change in the friction force, for example. So this is all classical conventional data analysis, I would say, and it is very, very powerful to understand what's going on in the experiment and to help you to get clean data. Another important aspect is that you should actually evaluate the data which you get on a cycle-based analysis. That means take one cycle after the other, look what are the periodic features and what are the non-periodic features, and then you can actually reduce the error bars or the uncertainty of your data in a great amount. And this, of course, will give you, for any later data analysis step, which will give you much more reliable and clean data, I would say. So that's what you can see on the right graph here, we have an example. We repeated the same experiment 10 times. We see that we get quite reproducible, let's say, values for the coefficient of friction. And if you would basically, what is sketched in the left graph, if you would understand that the blue data, the raw data are actually comprised of a cycle average and a periodic signal, then if you remove the periodic signal, then the noise gets reduced dramatically. Another very powerful tool which we developed in our company is what we call a 3D visualization of cycle data. And here, basically, what you can see is that you on one axis you plot the in-cycle position. In our case, it's simply the rotation angle of the disk, but it may also be in a linear oscillating test rig. It may be the position within one cycle. And on the other axis, you plot the cycle number. And then you can clearly visually see and also measure, of course, effects which are localized. That means which happen only in a certain position of the disk in this case, and which are transient in nature, which happens everywhere. And this is, to my point of view, very useful in any kind of tribometrical experiment to get a clear idea of what's going on in this experiment, and then of course to pre-process your data for further analysis in a good way. Yeah. So as promised, I give you the reference for this work. So it was published in Friction in 21, and it's open access. All right, so then let's continue with the next example. And this is now really about machine learning itself. So again, I would like to start with some motivating statement. So what we have here is basically a laboratory setup in a linear oscillating tribometer, where we test a self-lubricating journal bearing, which I will show you later, a picture of how that looks like, in an oscillating motion against the shaft, the steel shaft. And the idea is to mimic in this experiment the real-world behavior of this machine element. Here are highlighted some of the, let's say, the operating conditions. And what we have done is we have equipped this machine with force sensors, with thermocouples, and with a microphone to get data for algorithms which would actually detect states of operation later on. Yeah? So these experiments are here carried out by setting a certain threshold on the maximum force which we can transmit, and when this force is reached, it is stopped, and this is typically after 50,000 cycles, and we have 9 experiments. And that is what the typical output of such an experiment is prior to any classification or machine learning. So that means we get this time series data of for example, the coefficient of friction, of the temperature, and also the normal force or contact pressure in this case. And then one of our experts or a team of experts would actually go and start interpreting these results, and they would give annotations to that. So they would write here, for example, here's a critical piece of operation. Here's something happens with wear debris sticking in the contact. Here we have a zone of steady operation, and here we have a terminal failure. So that is typically how data could be labeled actually by an expert. And now the goal for machine learning is, what if we could train an algorithm which detects these kind of states, let's say automatically, and identify at least critical operating regimes early enough so that we can either, let's say, take countermeasures, for example, to add some lubricant, or if we could then stop the experiments at an early stage to actually investigate the root cause of such a failure. Yeah, what you can see on the right side of the picture are some let's say photographic images of the damages which we observe in this bushing or in this bearing, and these are typically scratch marks or wear debris sticking out somewhere, and this will actually lead to terminal failures, which are sometimes described as scuffing or yeah. And we would like to be able to stop the experiment at a time when this starts to happen, so that we can take out the samples from the experiment and we could then put them under a microscope or put them into a scanning electron microscope or do whatever, not to analyze what is actually going to happen here. Yeah, what we would like to do is to classify the state of the operation based on sensors which are already available on the machine. And what we would like to do is to let the expert actually give his input or her input on the classification scheme. That means provide labels to the data set. Yeah, these are the typical steps to go. I would not go into the details here, but just jump into the data labeling procedure. So what we had, as I told you, we had 9 experiments, each consisting about 50,000 cycles. So the goal was to label each individual cycle of each experiment. Of course, that is very tedious to do if you don't have any help for that. And we employed a procedure where we exploratively examine the data using PCA and k-means clustering to give us some pre-knowledge about what labels could there be, and then we let the expert adjust basically the labels based on his experience or her experience and end up with a labeled data set, which is shown on the right side of this picture. Okay, and then we tried 3 different approaches to actually classify this data. The first approach, okay, I forgot to tell you, okay, how did the manual labeling go? We actually plotted the shape of the friction data over each other and checked where are, at least from the visual inspection, where we can see differences, and then we would basically adjust the labels which were done pre-given by the k-means clustering algorithm. So yeah, so the first effort we made was using a random forest algorithm to train the data, to classify the experiments according to these 5 labels which we have given, or the 5 classes which we have given before. This is just a very short sketch of how we do that. I mean, I think for all of you who did some machine learning, the procedure is probably the same everywhere. So you take a test data set from 4 experiments, you split it into you take a training data set, so you split it into a training set and a test set, and you train a random forest classifier. You make a cross-validation against the test set and get some trained model from that. And the details are, of course, hidden more or less in the routines which we take. In this case, we take the scikit-learn library for Python to do that. And then to test or to check if the quality of the classification is satisfactory, we apply the trained algorithm to unseen data. That means we have, from our 9 experiments, we've taken 4 to train the algorithm, and then we take another one from these 9 experiments to test the quality of the classification. And here what you can see, this is a typical outcome of such a test. It's called a confusion matrix, where you actually plot or have a graphical representation of the prediction accuracy, if you want, of this classifier. And yeah, as you can see, the classification of the majority of the states is very good. So that means the steady state 1 and 2, which is the one which occurs most frequently in our experiments, are recognized very well or classified very well. And the other states, pre-critical and critical, are also, so that let's say the prediction accuracy is above 80% in all cases, which is for this system, I would say, quite a good score. Sorry. Okay, so to go on, as a next step, we took the microphone data and we tried a bit a different approach using what is called a variational autoencoder, which is actually a neural network, to try to detect at least two states, like which are called here normal and abnormal. So the normal states would correspond to what was called steady 1 and steady 2 before, and the abnormal state was all the rest. And we tried to use the microphone signatures to train an algorithm to predict when an abnormal behavior is happening. This was actually done in cooperation with our scientific partners from Switzerland, from the EMPA in Thun, and they developed the algorithm together with us. So let's say that the anomaly detection with a variational autoencoder will work after the following scheme. You have a variational autoencoder which consists of a layered network here, convolutional neural network, and you take, or we took, data from the normal regime signals, split it into 70% of training data, 20% of calculating a threshold, which would say then later on if the state is still normal or not. And then we took 10% for testing and mixed them together with signals from the abnormal regime to see if the algorithm can really discern between, let's say, normal and abnormal regime. The outcome is that the accuracy for prediction is 97% for the normal regime and about 80% for the abnormal regime. And yeah, this was, to our opinion, a quite good accuracy. Yeah. And the third, this was the last effort on this data set, which we did, is we go back again to the force data and we tried to check if we can achieve similar things with the force data, which are probably not as significant as acoustic data, but still much more readily available and more easy to process. So in this case, one of the students which we had was trying out a long short-term memory-based encoder-decoder network, which is again a deep neural network to learn the early onset of change in behavior. So the goal was here actually how much before actually the anomaly starts we could actually detect a change in the signal. Again, we split the data into training and test data sets. That's always basically the same procedure. And what we could actually see here is that about 5,000 cycles before the force signal would actually indicate abnormal behavior, this algorithm could already predict by a largely increased reconstruction error that something is going to happen. And this, of course, is, to my opinion, the right way or the right tool if we would like to actually start investigating our system before it is damaged too much. So again, we have 3 papers on that topic corresponding to these 3 steps which I just told you. So the first one is about the random forest classifier. the second one is about the microphone and the variational autoencoder. And the third one is about the long short-term memory encoder decoder. And these are all public, I mean, open access. So you can access them if you want. Okay, and now since I'm running out of time, I go to the third example, which I have prepared. And this now deals with engine oils. And the methods here are more on the classical statistical side. So again, starting with a motivation, what our colleagues from our chemistry or lubrication group observed in a long years of collecting data in field tests in passenger cars from engine oils is that about 1/3 before the envisaged oil change interval, the modifiers which are in the engine oil, which would actually reduce friction and prevent wear, they start to degrade or they start to disappear, if you want. And one of the most prominent additive in such a engine oil is what is called ZDDP. And this is an anti-wear additive which degrades by oxidation or partial oxidation and then loses its ability to prevent wear. And you see that in the chemical composition, which we use here to identify the state of the oil. I will come to that in a moment. But you also see it when you take this oil and do some laboratory friction and wear tests, you see that the friction force or the coefficient of friction and also the wear rate will increase when the oil is almost basically at the end of its life. And yeah, here are just some example data from our friction and wear tests in-house. So you can see that the coefficient of friction rises and also the wear volume or wear rate rises. And here you have also plotted the let's say the concentration of ZDDP in the oil, and of course, in contrary, the iron content in the engine oil will rise because of increased wear. And this is the observation on a qualitative level, and the motivation, of course, is then to actually devise some statistics or some procedure where you can model this data and give some more quantitative correlations between the different aging states of the oil. And one specialty which we have in-house is that we have put up some laboratory equipment where we could simulate this oil degradation under well-controlled laboratory conditions, what we call artificial alteration. And the question is, of course, always, are these artificial aged oils comparable to the natural degraded ones? That means which actually were destroyed in a car engine. And so that we have here a cooperation with Professor Filzmoser at the TU Wien, who is a well-known statistics expert. And with one of our joint PhD students, we are dealing with this topic here. Yeah, so we have oil samples from a passenger car, which were collected in a let's say in an operating range of about 20,000 kilometers. And then we have two different artificial aging setups. One is called small scale, which is just a laboratory device of this big, where you can probably age 1 liter of oil. And then we have a large scale reactor, which can operate a barrel of oil. Yeah, the chemical information is obtained in this case using a Fourier transform infrared spectroscopy, which actually measures absorption bands. And chemists, this is a very well-known procedure for chemistry, for lubricant chemistry, and the experts in the chemistry department, they can actually assign certain, let's say, products of the lubricant to certain bands in this spectrum. And this information should be used to devise some, let's say, quantitative correlation techniques. Yeah, so the first effort was to use more the exploratory, let's say, aspect of statistics, namely the principal component analysis, to check where the biggest variation in the spectra might be. And what we have seen here, this is a master thesis of one of our colleagues, that basically the first principal component, which explains something like 96% of the total variance, is very well correlated with the oxidation state of the oil. And when you compare that with a oil from a different reaction process, that also is true for this other oil, but the second principal component will show quite significant differences. And what we can do is we can project the data from one aging process to the PCA space of the other aging process, and then you get a very clear view on what is different between the two processes. And okay, I'm not a chemist, so for me this spectra would mean nothing, but a chemistry expert can tell you immediately what these two peaks, which are shown here on the black graph, what these two peaks would mean in terms of chemistry. So this is basically a tool to help experts to analyze their data, I would say. What we also did is we did employ partial least squares regression method to correlate our chemistry information with the wear and friction information which we got from the tribometers, and basically again the interpretation is up to the expert what that means, but the correlation is not so bad, I would say. And finally, we employed, let's say, more modern statistics methods like lasso regression to actually correlate the mileage in the field to some duration in our reactor in the laboratory. Again, as promised, here again the publications. I think this one is not open access, but all of you who probably have university access might download it. The master thesis of our colleague, and finally the latest paper about the lasso regression, which is published in Chemometrics and Intelligent Laboratory Systems, and this one is open access. Okay, so I will finally come to a summary and some conclusions. The summary, I would like to say that we have a few application examples here which demonstrates the various aspects of data science in our research, and AI and ML is only one of them. All examples are real data, so real data from experiments, and we always have the domain expert knowledge as an important input in our examples. The findings which we publish or which are reported here are limited to the specific system at hand, and we make no claims about transferability to other systems. Finally, yeah, our data science activities are motivated by practical research questions, as you have seen, and we do not pursue data science as an end in itself. We are users of data science, but we have good partners which are really experts in the field, and they help us to keep or to go beyond the state of the art in the methods which we use. Okay, and finally, some lessons learned as promised. Okay, methods and algorithms, as most of you know, we have huge sets of publicly available libraries like scikit-learn, like PyTorch or TensorFlow, which can help you to actually go about with AI, for example. They are not so hard to adopt actually, but the biggest issue is the availability of data, and that means you have to invest time and money to produce enough data to actually do big data in tribology. And you must also thoroughly prepare this data. So that means that is a time effort, a cost effort, which you should not underestimate. And to our experience, it is always best to use as much domain expertise as you can get hold of. And if you would like to plan ML activities on experimental data, then please check out the amount and quality of data and choose a learning strategy which is suitable for that. And also calculate, I mean, in terms of time and money, how the effort to generate this data. I would estimate that is about 90% of the total work on data science is about preparing the data. Yeah, and of course, try to get a ground truth and validate the outcome of your AI algorithm or machine learning algorithm. Okay, that's it. I have to acknowledge our research program, which is funded by the Austrian government and also by the province of Lower Austria and Vorarlberg. And yeah, an invitation in the end. We are open for cooperations, and if you're interested, please don't hesitate to contact us. Here are our coordinates. So just give us a call or write us an email. And that's the end of my talk. Thank you.
Thank you very much, Georg, for this very, very, very interesting talk and the lot of things that you showed there. So now for question time, I don't see any questions in the chat yet, but I do have one or two questions actually. So the one question is kind of linked to your last slide, and it's kind of two questions. So the one question is, how much data do we need? So if I am coming from the field where I am more in, so it's rolling element bearing, so then we already know for lifetime we do a lot of experiments to get statistical data, but they cost a lot of money, they run long time. So we say, okay, maybe 5 experiments with 4 bearings per experiment, then we say, we can start to trust the data, but if I have to train some machine learning on this, I think this will not be enough. So how big a data set would you say is the minimum I would need to start doing this? Yeah. And then just as an add-on, do you see any chance of a lot of the historical data that is available? So be it in an institute, that experiments that have been done, or other data available publicly can be, let's say, included in this without problems? So there's actually 2 questions.
Okay, so then I will answer the second first, because that is more, I can give you a better answer on that. So the historical data sets are fine as long as you have good metadata. And that is the but here, because at least I know it from my institute or from our institute here, is that you always do experiments on a specific purpose. And you normally don't think about a more general, let's say, afterlife of this data. And that means when you come back 10 years later and you would like to address a specific question and you look at this old data, you probably miss the crucial information because it has never been recorded. And people tend to forget, and you can start searching in old reports or old publications if you find still some useful information. And that costs you an enormous effort. Yeah. So that is what we learned ourselves. And our strategy now is, when we plan experiments for any project, actually, that we try to record or to be as clean as possible in the notation or the annotation of data with metadata, and also the point of managing those data. That means, where do you store them? How do you store them? Do you actually record the the storage format? Do you have the software to read them in later on? And all these aspects are actually crucial for using historical data. And to my experience, if you have not been very careful in producing that data at the time you produce them, this historical data might not be very useful. So that's probably more a matter of quality management or foresight, if you want. Yeah, so that, yeah, if you're lucky and you have an institute which has a long history of good quality metadata annotation, then you can use this data. Yeah? And the other thing concerning how much is the minimum data set necessary, I would say the more expert knowledge and the more physics you put into your learning strategy, then the less data you need. Yeah. Okay. So yeah. I cannot give you an absolute number, but I mean the recent developments, what we are also looking at is what is probably called physics-informed or hybrid modeling or physics-informed learning. Also labeled or supervised learning might be more suitable in this case if you of tribological data, or let's say data from such tests. Lifetime tests are extreme case where you have to run experiments a very long time normally, and you get only a few basically lifetime points in the end, or you even try to use well-known classical statistics instead of machine learning, yeah, to access information about your data.
Yeah, thank you very much. Yeah.
Okay, I have to repeat that what I just said because I was muted on the stream. We have a couple of questions in the chat now, and I want to first relay a question from Nick Garabedian, who gave a flash talk together with his student Ilya Barbon. I don't remember the last name of Ilya. Sorry, Ilya. But basically, I think this is very suited also to the whole topic. Maybe you should go to YouTube if you have not yet checked it out and listen to those flash talks. And he asks, "Hi Georg, that's an awesome collection of works. Where could we find the data and code associated with the papers that you presented?"
Okay, good. The data in our institute. So, yeah, I mean, we could think about sharing the data if we could find a way of collaborating, I would say. The point is that this paper were recorded with this data were recorded with an industrial partner, so we have some kind of confidentiality requirements here. But probably we can, if we can talk a bit in person, we could probably find a way of sharing that data under certain conditions, which means, for example, scientific cooperation. The code is in our institute. We have currently no intention of making it public in a way that is not because we don't like to make it public, but because the effort in documenting it correctly and making it useful for the community is not where we have currently budget for. Still, what we are using is as I said before, is standard publicly available libraries as for example, scikit-learn, PyTorch, and TensorFlow. Yeah.
Okay, then relating to that, I want to do a couple of questions by Vivimat, which I think might be Stefan Eder. So first of all, answering this question, he says there is actually an existing contract between AC2T and the Karlsruhe Institute of Technology where Nick works, so maybe you can work something out there.
Okay, perfect.
So NDA should not be a problem, so maybe you can get together.
Yes.
And then there was another question from probably Stefan. If one wanted to contribute some existing data to such an evaluation, what would be the minimum requirements with respect to self-consistence?
Yeah, I mean, the expert should actually have a educated guess on what is outliers, what is reproducibility of the data. So you should have at least a few repetitions of the same experiment. We have actually not yet established a quality measure. We are working on that, and this is a hard topic actually to actually assign a number of, let's say, a confidence level on, for example, the coefficient of friction or something like that, because we know from our past that tribometric experiments might exhibit a lot of outliers, a lot of variation in the data. Even using the same machine on different institutes, we have some kind of round-robin tests for SRV tribometer, for example, which produce a very high variation in the when you go from one institute to the other. I mean, what we would need to do probably is to train an algorithm on a mixture of experiments from different institutes to get it suitable for the data at hand. Yeah. So what we did, for example, is that we mix the data from 4 different experiments into one training set in order to make an algorithm which is more capable of predicting outcome of unseen experiments, which are hopefully within the range of the seen experiments. Yeah? So that's hard to answer. We have to define a use case where we collect data from different institutes to see what is the variability, and then to define a certain window of let's say levels of data where we can work with. So I think the biggest problem with this AI and ML algorithms is once you go out of the defined domain of the defined data set, yeah. So the extrapolation quality is, I mean, I would say questionable at least, yeah. So if you go away to a different domain or outside of your domain of where you trained your algorithm, then I would highly doubt that you're, at least at the state where we are now, that an AI or an ML algorithm can actually give you useful predictions. Yeah. So we have to define the range of parameters where we work first, and then we can contribute data from different institutes easily if we are within this range. Yeah.
So maybe another small question from the chat, also from Vivimat. So are simulation results better suitable as they are more likely to have useful metadata?
Yes. How? Yeah. I mean, that's another thing which we are currently working on, and the question is how you would. I mean, I know that there are efforts, for example, in the DFT community to use AI to predict structures or energies from a few, let's say, cornerstone DFT calculations. So you are much more expert, Michael, than me on this field. So yeah, we can try it out with I mean, what would be the variability in the input of your data when you use simulations? Yeah, so you have to do some variation. For example, when I would think about FEM simulations of machine components, for example, then I would vary some tolerances in the construction, for example. Yeah. So if you have a bearing and a shaft and you would like to study the outcome of a simulation under the variation of construction tolerances or fabrication tolerances, for example, yeah, or uncertainties in the material parameters or something like that. Yeah. Otherwise, I mean, a FEM simulation is a deterministic result. You will get always one result, and why use an AI algorithm for that then afterwards? Yeah.
Yeah, that's, I think, very good. Thank you very much, Georg, for these answers. I think we don't have too many other questions. I still have some questions, but I think we can discuss them maybe in person at some point when we meet. And then I would just say we can continue onwards with our program. So let's thank Georg once more for his great talk. And then we will move on towards the
Yeah, I will stop sharing my screen, yes, and I will say goodbye at this point and hand over to my colleague. Yeah.
yes, exactly. So that's